So I'm going to derive the law of sines. I'm going to do it by doing a pretty standard problem in a way we totally know how to do already. And we'll do it with numbers, and then we'll notice a shortcut, and then we'll rewrite that all with letters. And the problem is we're going to start with knowing side AC, 27, BC, known to be 20, and one angle, angle A, is equal to 47 degrees. And the goal is to find angle B. And our technique so far for this has been to utilize an altitude, say H here, and go through H and to get from the left-hand side right triangle to the right-hand side right triangle. So we'll do that, but then we'll notice at the end that we can actually talk about it without mentioning H. So it seems key, but will be discarded at the end. So what's the first thing we could do? We're going to try to find H, and that's going to be with a trig ratio. H over 27 is going to be sine of 47 degrees. And so H is 27 sine 47 degrees. That's great. Let's go ahead and get that. Not hard to calculate. And that is 19 point. Let's keep some accuracy there. The main thing is we're going to be looking at a derivation of something with letters. But anyway, okay, so that's our height. Okay, and then very similarly, but just a little backwards, is we can say the same kind of thing about sine B. So sine of that unknown angle, well, that is that very same altitude divided by the hypotenuse of the right-hand right triangle. Okay, and so that's going to be, let's evaluate that. It's pretty close to 1. That's pretty close to as big as a sine can ever get. That's maybe a little more accuracy. Okay, and then so B is going to be the inverse sine of that. And let's compute that. Okay, the calculator gave me 80.622 degrees, and maybe we could like round that to like 80.6 degrees because it's unlikely that we'd want it to such precision. Okay, really pretty straightforward. Not something that's any beyond what we've been able to do. But I want to notice that notice because that altitude kind of came in and then immediately got used up and pushed into the calculation for sine B, we can write this in a way that doesn't actually mention the altitude. So let's see what happens here. If we go back to we'll go back to the start and just do the letters. What do we have? We have H over B was equal to sine of A. That was the first step. And of course, we solved that for H. And we thought, oh, that's because we have to find the number H in order to go to the right-hand triangle. But let's see what happens. What did we use on the right-hand triangle? We used that H over A was equal to sine B, just exactly the statement of the definition of the sine ratio for the right-hand right triangle. That says H is little a sine B. And then here's the key thing. I can eliminate H here. If I don't really want to highlight H, which I didn't really care about in the start, I can just set these two guys equal to each other. Right? That's a pretty common but still very useful technique that I can eliminate a variable. If it's isolated on one side of two equations, I can just set the other sides equal to each other. And it turns out that that is part of the story of the law. That's the essential part of the story of the law of sines. That little b sine A, so remember little b is always, in this convention, is going to be the side opposite angle B, and little a is going to be the length of the side opposite angle A. And we've got a rather nice, pretty form, and it doesn't mention H at all. And there's a couple of equivalent forms for this. We could divide both sides by both little a and little b, and that turns into sine big A over little a. On the left-hand side, when we divide this by little a and little b, the little a cancels, and what comes up on the right-hand side is little b. If you take the reciprocal of both sides, this can be sometimes cool. The way you most often see it is this form, but they're all equivalent. These are the law of sines. Now I'm going to say a little bit more. I'm going to extend this just a little bit more. But we've got the basic idea. Okay, so let me go ahead and redo the problem. It's not going to be a major shortcut here, but once you know this and you can use it in a flexible fashion, it is a nice significant shortcut. So let's redo the original problem with basically one step fewer. Okay, we are just going to write down the law of sines. Let's write it down this way. Suppose we've memorized it in this way, and we just put in what we know, and we leave as a variable what we don't know. Sine 47 degrees over 20 equals sine of b, that's what we want to find out, over 27. Just instantly we get one equation with one unknown, the thing we want to figure out. We of course do have to do some algebra. So sine b, if we multiply both sides by 27, we're going to get that this is 27 sine 47 degrees over 20. I usually like to write that with the trig part kind of isolated. Oops. And then we note that that's modified by taking a ratio of sides. So we take the sine of one of the angles, and we get a ratio of the side that's opposite B, the new angle, divided by the side that's opposite this angle, the angle 47, right? And so this is going to be a familiar number. Let's make sure. Okay, that's that 0.98733 that we had before. And then the last step is just the same. It was to take an inverse sine. So that's not going to be different. Okay, so this is a nice shortcut for this kind of problem, and then it gives shortcuts for a lot of other kinds of problems, because once you've discovered this, even though it was in a particular context that we figured out that this was true, this is a universal rule for triangles, and it doesn't at all rely on the whole big triangle being a right triangle. It is a universal rule for all triangles that sine A over A equals sine B over B. Let me just extend that a little bit. I happen to be focusing on angles A and B and their opposite sides. There was nothing special about that. I could have run the same argument to relate B and C. I would have used a different altitude, but who cares? The altitude didn't show up in the formulation, the eventual formulation. I could have related A and C to each other. And so just based on kind of a basic symmetry principle, essentially, what we can say is that if I had focused on B and C, I would have gotten an equation that said sine big B over little b is sine big C over little c. So I would have gotten this equation if I had just focused on B and C. If I had focused on A and C, I would have gotten this equation. Well, guess what? If they're all true, then all of these things are equal to each other. That's actually very nice. It's very, very symmetrical. So it's a very symmetrical principle. And it's easy to remember. It's easier to remember than the law of cosines, if you've seen that. It's just take the sine of each angle divided by its opposite side. Those are all equal to each other. And in another video, I'll show you another way you can apply this to a bit of a different looking problem.